Okay, so yeah, just to introduce me, I'm an assistant professor at the University of Texas. Where my group and I am working on the development and application of enhanced sampling methods. In particular, working on enhanced sampling method based on like collective variables. You can see, where is this? This is my. Okay, did I not remove? Sorry, just trying to do one thing. Okay. Okay, as Michael was talking about yesterday, we have this kind of timescale problem in atomistic simulations. Is that we have this disparity between the fast processes and the long timescale phenomena that we are interested in. And like conventional molecular dynamic simulation suffers from a severe timescale problem. And this can be kind of understood by the fact that we have like this different metastable states separated by high free energy barrier. The time it takes from average to go between the two metastable states scales as the exponential of the barrier height divided by the thermal energy. So if the barrier height is much higher than the thermal energy, it will just be trapped in a metastable state. So we need some kind of more advanced sampling methods to overcome this and bridge timescales. And this is what we're going to talk about today. So there's a wide range of enhanced sampling method, and this is actually something that we try to do in this paper with Michael and others, where we try to kind of characterize the different enhanced sampling methods. And this is this paper shown here, and the link is here, like the link is shown here. And we try to kind of characterize the different enhanced sampling method. So if you're new into the field, I really recommend to read this paper because it discusses a lot of different methods and also has a nice glossary to understand, to introduce many of the phenomena and concepts that are used in the discussion of these methods. Here, we'll be mostly talking about these methods like here, which are so-called collective variable-based enhanced sampling methods. Some other resources which I think is very good to read would be like this review paper, the review paper of metadynamics, which I wrote a few years ago. And I also listed here other reviews of metadynamics, which is good to have in mind if you want to understand a bit more on the theory of metadynamics. In this lecture today, the theory will be mostly based on the similar discussion as in this paper here. So the notation will be the same notation as used in this paper. Okay, so what do we do in this collective variable-based sampling method? We start by mapping the problem to a lower dimension. Of course, initially we have like the high-dimensional configuration space, which is of course very high-dimensional and hard to understand all the different atomic coordinates. And now we introduce some collective variables, which are like some coarse-grained descriptor or order parameter that can be like non-linear function of the atomistic coordinates. So these collective variables are normally like much fewer in number. Generally, we are using maybe 1 to 3 collective variables to understand the system. So the idea that we do here is that we identify a few important coarse-grained variables that describe the problem at hand. And by describe the problem at hand, I mean that they distinguish the relevant metastable states and include the slow degrees of freedom in the system. And normally this would be done by using kind of physical intuition or chemical intuition. You kind of look at your system, try to identify some collective variables, then you define these collective variables, you monitor them and see them if they can distinguish the different metastable states and so on. Normally this is a quite iterative process that you need to try different collective variables, see how they behave, try another set of collective variables and so on. And there are a large number of generally applicable collective variables available. Just to give you a few examples, the most simple case of collective variable would just be dihedral angles, like shown here. Then we could have something like distances, like just distances between two atoms in a molecule and so on, or a protein. Or we can have something more complex, like a root mean square deviation from a reference structure, or like a coordination number that measures like the number of hydrogen bonds or the number of kind of like the atoms that are coordinated in some system. There is one feature when you look at coordination number with collective variables is instead of having like a sharp cutoffs for like measuring if two atoms are coordinated or not, we don't use that. We use a continuous switching function to describe the coordination, something like here. And this is something like we would have like that here there would be like value of 1, and then then it would have value of 0. Then you have some range which kind of the switching function slowly goes from 1 to 0. And this has to be a continuous function because it will be used to bias the system using molecular dynamics, and we need to have continuous forces for that. So this is something which we always need to use as this continuous switching function. And then you could have something like the radius of duration, and there are many more different collective variables. If you can just look at the Fluent manual, which is the code we're using here, there's a wide range of collective variables available, like just shown here. And furthermore, you could have, let's say, you can define collective variables. There is a function of a different collective variables. So through many kind of like different combination, you can define quite complex collective variables. Okay, so now when we have defined these collective variables, we can define like the free surface corresponding to these collective variables. Okay, we start from the Boltzmann distribution shown here, and then we obtain the marginal distribution of the collective variables obtained here by inserting this delta function with the Boltzmann distribution and integrating over all other degrees of freedom. So this will be the marginal distribution of this collective variable. And in principle, the marginal distribution is nothing but the expectation value of the delta function. And then we just normally look at the free surface, which is given by the negative logarithm of this probability function with energy scale given by the kbt, or 1 over beta. Okay. So in this way, we have mapped the problem to a lower dimension by going from the potential energy surface, which is like high dimensional and rigid, to the free surface or free landscape, which is like low dimensional and normally smooth. So the idea behind this collective variable-based sampling method is use this collective variable both to represent and drive the sampling of the free landscapes. And the free surface is normally what we are interested in obtaining, because it gives information about metastable state, the relative stability, and free energy barriers. Okay. In principle, we could estimate the free surface directly from an unbiased simulation, meaning we could define the free surface just as a, let's say, in the following way here, where this n is a normalized histogram. So we could just like run the simulation, count where this collective variable is, and just obtain like a histogram of that. And then we can just take the log of that, and we can obtain the free surface. So in principle, it should be possible to estimate the free surface from the histogram accumulated in an unbiased simulation. However, as we shown yesterday in the Michael's example, this rarely works due to sampling problems. Most of the time, we're just like vibrate in one metastable state without ever seeing a transition to another metastable state. So we need some more enhanced sampling method, something to improve this. And this is the idea with this like CV-based enhanced sampling method. And the idea that we introduced a bias potential that acts in the space spanned by the slow collective variables. And this was kind of originally suggested in umbrella sampling. So the idea is that, okay, here we have like the unbiased system with 2 metastable states, like with a high free energy barrier. And now we introduce some bias potential so that the barrier between the 2 states is reduced. So it's easy to move between the 2 metastable states. So this is like if you look at the free energy landscape, but equivalently, we could look at the probability distribution. So what we're doing when we introduce this bias potential is that we're enhancing the fluctuation of these collective variables. So we go from, let's say, a biased distribution, an unbiased distribution like shown here, where like there's like where we have like no like probability in between the 2 states, and like there's very unlikely to go between the 2 states, to something like here, where now we have like enhanced the fluctuation of the CVs and make it likely to go between the 2 metastable states. So mathematically, this can be shown like here, that we introduce this bias potential that acts in the space spanned by the slope collective variables, and we sample this easier bias distribution, which is shown here. And then this biased CV distribution is just given in this equation like here. So it's basically like we add basically the bias potential to the fringe surface. So this is, let's say, the biased CV distribution. Okay.
If I could jump in, I just want to draw some connections. Like this is exactly what we're talking about reweighting to remove the effect of the bias. It's the exact same equation. See the Boltzmann above and below of the bias. So
yes, exactly. I mean, it's the same. And that's exactly what I was going to talk about next would be, let's say, reweighting.
Sorry to interrupt.
Because of course, naturally, when we do this kind of biasing, we have a different system. We don't have the original system. So we want to get the equilibrium properties of the system. And that we can do by using this kind of like reweighting procedure, where you can just reweight any observable in the unbiased simulation in this way here. So you take this as an observable in the unbiased simulation or the original system that you want to obtain, and you do that just by calculating the corresponding observable in the biased simulation. But to each sample, you just add this weight here, and this is a sample average in the biased simulation. So then you also need to put this here to make sure that this is still normalized. So this is, let's say, how you can do this reweighting. And in principle, you can also get the fringe surface for any given collective variable. So let's say if you do a bias simulation with some given bias potential, you can obtain the fringe surface correspond to some other collective variable, but just by doing a weighted histogram, where you do a histogram as before, but now you add a weight to each point in the histogram. So you take into account how much bias was acting on its sample when you obtain the sample. And we will see in the tutorial example where we do this in meta-dynamics. Okay. So now the question is like how to select a good bias potential. So here, let's assume that we can take the bias potential in its following form here, where this gamma is some parameter which is larger than 1. We will see later on how this parameter comes into well-tempered meta-dynamics. So this is, let's say, we assume that we could design somehow a bias potential of this form here. So it's basically the negative of the fringe surface, but with this factor here in front, 1 minus 1 over gamma. And if we insert this into the bias CV distribution, we get this equation here, which is the so-called well-tempered distribution. And okay, so you can see that some of what we're doing here is that we're taking the initial unbiased distribution of the CVs and we're kind of making it flatter, something like this. So basically, this gamma factor determines how much we flatten the distribution. So if gamma is 1, we will just get the same equilibrium distribution. But as we increase gamma, this bias distribution will be flatter and flatter. In other words, we are enhancing the fluctuation of this collective variable. Okay. And one can also see, which is good to have in mind when doing well-tempered meta-dynamics, is that if you insert this, let's say, this equation for the bias distribution into this equation here for, let's say, an effective fringe surface in the bias simulation, you can see that like when we're using this well-tempered distribution, we're basically sampling an effective fringe surface where the barrier has been reduced by a factor of gamma. So you can think in a way, let's say if you have barriers that are on the order of 10 kpt. In this case, we should probably choose a gamma value of, let's say, 5 to 10, because in that case, we would reduce the barriers from 10 kpt to 2 kpt or like 1 kpt. So you should use like an optimal this gamma factor such a way that the effective barriers are around a few kpt and easily crossed in like a more dynamic simulation. So this is how you can think of this well-tempered distribution, that you're either, let's say, enhancing the fluctuation of the CVs, or you're basically reducing the barriers on the effective biased fringe surface. And then, of course, you can take the limit gamma goes to infinitive, and then you would get basically directly like the bias is just a negative fringe surface, and you basically get a flat histogram or a uniform sampling of the CVs. So there are many enhanced sampling methods that aim to achieve such a flat histogram bias, but generally, in my opinion, this is not optimal because you spend a lot of time sampling regions high in free energy that are not relevant, and it's better just to enhance CV fluctuation with a finite value of the gamma factor. Naturally, we come to the question is how can we do this? Because you can see that this bias potential that we're talking about here depends directly on the underlying fringe landscape, which is exactly the very quantity that we want to obtain. So we cannot use this directly because if we could use this, we would already know the answer that we want to obtain. So nowadays there are many methods that can build on the fly a bias potential that can give this solution. So in case that they can there's kind of through some iterative scheme, they can construct a bias potential that in the long time limit converges to this equation here. And in particular, we'll be talking about meta-dynamics, which is the method that we'll be talking about today. Other methods is variational sampling, which is a method I'm developing, and also OPES, or the on-the-fly probability enhanced sampling. And these are all methods that are available in Bloom. But today we'll be talking about, let's say, meta-dynamics. But maybe I want to say a few general requirements of these collective variables, which are quite general for any given collective variable-based method. Normally, when we select this collective variable that we want to bias, they must be few in number. Most methods cannot really handle more than maybe 1, 2 to 3 collective variables. Although there are some extensions that allow for overcoming this. When we use this method for molecular dynamics, we must have continuous forces. That means that these collective variables must have continuous derivative with respect to the atomistic coordinates. Because when we use them in for molecular dynamics, we need to calculate the biasing force, and for that you need to use the chain rule, and at the end you need to calculate the derivative of this collective variable based with respect to atomistic coordinate, and that has to be done in a smooth way. This is, for example, why we use this switching function when we use anything that is a coordination number. And they should distinguish all the relevant measurable states. And also they should include all the slow modes of the system. Of course, this is not always possible, but there are ways to tackle this if this is not fully fulfilled. Okay, so in meta-dynamics, the idea that we use there is that we run a simulation, and then periodically you deposit a repulsive Gaussian biasing kernel where you're at the current location. So basically it's something like this figure here. Here in the unbiased simulation, we have a high fringe barrier that we cannot overcome. So in meta-dynamics, what we start to do, we start to deposit these Gaussians in the collective variable space so that we can more easily overcome the barrier. And in this case, when you deposit enough bias, you start to go to the other metastable state, and you start to see frequent transition between the two metastable states. So the idea you deposit these Gaussians, and this pushes you over the barriers. So the most common method for meta-dynamics nowadays is so-called well-tempered meta-dynamics. And this is, and now I'm going to talk about the theory behind well-tempered meta-dynamics. And that is basically through this iterative process discussed here. So what we do now is that, as I say, we periodically add this Gaussian to the bias potential, and we do it in this following way. So this, let's say, is the bias potential at some step n. So we now add a new Gaussian to the bias potential. That is this term here. And so first we have the previously added Gaussians, and then we add this Gaussian here. And this, let's say, term here is a Gaussian biasing kernel, where we have some given height, WO, 0. And this is centered on the current CV location. But now we not only like deposit Gaussian directly, we also scale the Gaussian with this scaling factor here. And this like scaling factor here depends on this like gamma factor, which is the same gamma factor as before. And in meta-dynamics, this gamma factor is called the biasing factor. And this biasing factor determines how much we enhance fluctuation. So basically the idea is that, let's say, to recapitulate, is that we like periodically we add this Gaussian and we scale the height of the Gaussian with this factor here. And so, and we always do that like the current location that we are currently at. So this update is performed like every ng steps. Normally you would do this maybe every 500 to 1000 molecular dynamic steps or something like that. And then between updating these steps, the bias potential will be written this following way here, where this this factor here is the height for the Gaussian deposit on step K, as shown here. And you can see that, and you can see one thing to notice that I forgot to mention is that the scaling factor depends directly on how much bias we already added at this place. That means that if we have added no bias to the current location, this scaling factor will just be 1. So it means that we just add the Gaussian with a full height. But if you added a lot of bias to the current location, meaning that if there are currently a lot of bias on the current location, the scaling factor will be much smaller than 1. So as we kind of start to deposit Gaussians, this height goes to 0. Okay. So we need to keep account of this, like the height deposit, like the Gaussian height for the Gaussian deposit on step K. So this is the current bias potential. So it's just a sum of Gaussians with different heights, and the heights depends on how much bias there was when we deposited that Gaussian. Okay. And it can be shown that this like scaling factor in the update shown here decreases to 0 as like 1/n. And that means that as we increase this, like simulate longer and longer, the height of the added Gaussians goes basically to 0. This means that the bias reaches a so-called quasi-stationary state, meaning it's not changing much with time. And this is important for the reweighting, as we'll see later on. So one can kind of show in the long time limit that this bias fulfills this equation here. And this is basically the same as the well-tempered distribution that we showed before. And where this K of T is a constant independent of the CVs. So one can show in well-tempered meta-dynamics that in the long time limit, we obtain this well-tempered distribution. So basically this bias factor that is a parameter in the meta-dynamics determines how much we enhance the fluctuation. And we can also see that through this equation here, as we have the bias potential from the simulation, we can directly obtain the fringe surface just by calculating the bias potential, calculating the fringe surface from the bias potential as shown here. So we can always obtain the fringe surface directly from the constructed bias potential. And this is a prototypical example of a well-tempered meta-dynamic simulation. So you can see here, like here we have some collective variable. So we like start in this state here, then we go to the other state, we start evaporate a bit that state, go to the other state, and then continue. And you can see here that, for example, this red area is the amount of bias deposited after 50 Gaussians, then the green is like 400 Gaussians, and then you can see like when we go over the other state and sample that, then we have like this yellow range, the orange range, which is like we have obtained like 1200 Gaussians, and then we converge to something like here, where we have like a much reduced bias. And in this case, we like this gray area is the initial distribution, while this blue area is this well-tempered distribution. And you can see here clearly, like this, what I show here is the Gaussian height. So you can see here, like when we're in this area, we're just depositing Gaussian in this state here. And like we can see that the Gaussian height is going down because like we have deposited a lot of bias there. But now we go to the other state. And once we go to the other state, there is no bias added to that state. So we can see here that suddenly the Gaussian height goes back up to high value and then slowly decays to 0. And then once we have enough transition between the two states, we can we convert the simulation. There's one issue with well-tempered meta-dynamics is regarding reweighting. Is that now we have a time-dependent bias potential, so we cannot use this like reweighting procedure directly. So now we need to account for the time dependence of the bias potential when reweighting. That can be done by using the so-called C of T factor. So the C of T factor is calculated as shown here. And this is, let's say, a time-dependent constant. As a time-dependent constant that grows during the simulation. So you can easily reweight meta-dynamic simulations using this time-dependent constant if you calculate this time-dependent constant. And we will see, there will be an example in the tutorial where we'll do this. So in some sense, you can, let's say, look at this like bias potential minus the C of T as a renormalized bias potential used for the reweighting. And this, let's say, the calculation of this C of T is implemented in Pruned, so you can directly calculate it on the fly during the simulation. And we will see that later on how you can do this in practice. Okay. Yeah. To say, in the original version of meta-dynamics, the bias kernel was not scaled. So this corresponds to like the limit of the bias factor goes to the infinitive and a flat histogram. And this is generally hard to converge. So like normally I would recommend using this well-tempered meta-dynamics because this normally is better and has better convergence properties than original meta-dynamics. In original meta-dynamics, what people sometimes do is that they use like a time average of the fringe surface, obtain the fringe surface from a time average of the bias potential. But generally, I would recommend using the well-tempered meta-dynamics. Okay. Okay, so let's take an exemplifying system of alanine dipeptide. This is a very simple system. Then alanine dipeptide in vacuum, and here we have the backbone dihedral angles as the relevant collective variables. So in this case, we use like the psi and the phi and the psi variables shown here, and we have like two metastable states. These two metastable states shown here and here. And here the barrier is around like 16 kpts, and the transition time is around 28 microseconds. So here we can see like an unbiased molecular dynamics simulation of like of 3000 nanoseconds. We see maybe one transition between the two metastable states. So it's a very rare event. But now when you start to bias this collective variable, and here I'm only biasing one of these collective variables, the psi variable, and you can see that we have a large number of transitions between the metastable states. Sorry, I'm biasing the phi collective variables. That will be important later on to distinguish between that. So you can see here in this like blue, this one here where I'm biasing the phi collective variable, is that we have a lot of transition between the two states. And now we can see there's a factor of 300 in the time scale. Okay. So this is like an example where like meta-dynamics is like very efficiently enhancing the fluctuations and in the sampling of the system. So as I say, this reweighting, we can use that to obtain both for the fringe surface, for the fringe surface for the CVs that are biased, but we can also use it to obtain fringe surface for CVs that are not biased. For example, in this tutorial later on, what we will do that we will obtain the fringe surface directly from the bias potential and also from reweighting and compare the results. And this is really a good check for convergence of meta-dynamics. Is that what you should do when like looking at meta-dynamic simulation? You should, let's say, calculate the fringe surface directly from the bias potential, and then also calculate it through reweighting and compare the results. And if they give the same profile, you're in good shape, and probably they're giving good accurate results. But if they're very different, most likely you have some issues with your collective variables or some other issues in your system. But what's also useful for this reweighting is that you can use it to obtain the free intersurface for collective variables that you're not biasing, like shown here. Like here, we obtain the free intersurface as a function of the distance that we're biasing, and we also obtain the free intersurface for the coordination of the sodium atom with the oxygens. So we can obtain this two-dimensional free surface through reweighting. Okay. And you will see an example of this. Some example of some extension of meta-dynamics that have been developed. I will maybe not go through all of them, but just mention them, like parallel tampering meta-dynamics help the sampling missing slow collective variables, or well-tampering the sample can be used to reduce the number of replicas needed for parallel tampering. And also, let's say, multiple walker simulations, but the idea is that you have multiple walkers running at the same time, where you have like the multiple walkers share running meta-dynamic simulation, where you share the bias potential between the simulations. And this is something that will be done in the tutorial tomorrow. And also, like, you have adaptive Gaussian meta-dynamics, where you like the Gaussian adapt to the shape of the free intersurface. And also, like very useful extension is the so-called infrequent meta-dynamics. And that is the way for obtaining kinetics of rare events from bias simulations. So you can see, like, if you look at this review, you can see further information about this extension and the original references. You can also see the same discussion in the i-CoMSE review that I mentioned in the beginning. Okay, let's say the code that we use for meta-dynamics is Plumed. And Plumed is like a plugin for molecular dynamics codes. It's open source, has a wide range of collective variables, and implements a wide range of enhanced sampling methods. And in my mind, it's very easy to use. And also has an extensive number of tutorials. And you can use Plumed with many different MD codes like Chromax, LAM, CP2K, and it's very easy to interface new molecular dynamics codes with Plumed. Okay, so yeah. So maybe just briefly mention what are the input parameters when you are like start a molecular meta-dynamics simulation. So you normally have like 4 input parameters that you need to select. First of them is, let's say, is like first is just how often we deposit Gaussians. This is like how often we deposit Gaussians. You cannot do this too frequently, but normally, so say a value of like 500 to 1000 is fine for molecular dynamics simulation. Then you have the initial height that goes into like the initial height of the Gaussians added. And then you have the bias factor that determines how much we enhance fluctuation, but it also determines how fast we convert the simulation. And then we have like the width or the standard deviation of the Gaussians. This is basically for each collective variable, how wide the Gaussian is that we add. And so this comes into like into the Gaussian kernel here. So here I mentioned some typical values for this parameters, like for, let's say, the how often we add Gaussians, maybe 500 to 1000 molecular dynamic steps. And then like the height, normally you would take a fraction or around kpt. For example, you could take something like the 1/10 of kpt to, let's say, 1 kpt, or maybe half a kpt. That are reasonable values. And then, okay, then you would select the bias factor, and ideally a value that makes the effective free interbarriers to be an order of a few kpts. Of course, this is something which you don't know a priori, so sometimes you need to do a bit trial and error to find good values. Because what you will see is that if you use it too low, you will not enhance the sampling enough, while too large will lead to slow convergence. And then, like this width of the Gaussians, or the sigma values, they should be in the order of the fluctuations, in other words, the standard deviation of the CVs observed in the unbiased simulation. for example, 1/2 to 1 of the unbiased fluctuation. But I will show you an example how we will estimate this in the notebook. And then let's take another exemplifying system, which is just a Muller-Brown potential. It's a very simple system. It's just a one particle and two-dimensional potential energy surface with the function shown here. And this is the fringe surface. And we have a barrier around, let's say, 20 kpt. So we just have like one simulation, one particle on this surface. And in this case, we're using X and Y as collective variables. So the phase is just given by the underlying fringe landscape. So I will show you, use this as an example to show a bit the effect of the bias factor. So, okay, if we just do unbiased Monte Carlo simulation, as shown here, we'll see that we see no transition between the two states. We start in the space in here, and there's no transitions. Or there's maybe one transition, but we never go back to the initial state. So it's very rare to see transitions. So now, if we kind of do this metadynamics, we start to see a lot of transition between the two metastable states. And if we, let's say, look at the estimate for metadynamics, it's in good agreement with the exact potential. But now let's say, look at the effect of the bias factor. So here, for example, here we have, let's say, bias factor of 10, and we can see this is like the region that we sample in the simulation. While at bias factor of 5, we can see, okay, the reason that we sample is less, because that makes sense, because we are enhancing the fluctuation much less. But now we can see that this is, let's say, something. But this is really misleading, because if you look at the time series, what you can see here is that while the bias factor 10, we can see a lot of transition between the two states. With a bias factor of 5, we just see one transition, and then it never goes back. So in this case, a bias factor of 5 was not sufficient to overcome the barrier. And that makes a bit sense, because in this case, the barrier is around 20 kpts. So like a bias factor 10 reduced the barrier around like 2 kpt, but 5, maybe 5, then we have like 4 to 5 kpt barriers. So it's still a bit slow system. So finally, maybe just an example, let's say, what happens if we're missing slow collective variables? And in this case, let's look at island dipeptide again. So in this system, if you look at this fringe landscape, you can see that you can discriminate between the two states by using this the phi collective variable. While psi does not discriminate well between the two metastable states. In other words, this psi collective variable is degenerate. Because you can see, like, if you take a value like here, this can correspond to two different metastable states. So in this case, phi is the slow collective variable and psi is the fast collective variable. So, okay, we bias only the slow collective variable, phi, everything works fine. We see a lot of transition between the two states, and like it converges fine. So but now we do another test where we bias only the slow fast collective variable psi. So in this case, we're biasing this collective variable here. We see some transitions, but they are only just to kind of random fluctuations. But what we see here in this collective variable behavior here, we see this like hysteresis behavior. Is this start to see like overlap in the two values. We see like hysteresis behavior here, like it grows and then it goes to the other state. But it like there's overlap in these two between the two states. So in this case, the simulation will not converge to anything meaningful. So maybe finally, I'll just mention one, let's say, extension that can solve this, is that in principle is to combine metadynamics with well-tempered metadynamics, a well-tempered simulation, or other replica exchange methods. Because here you kind of reduce the requirement of the quality of the metadynamic CVs, as the parallel tampering will help sampling the slow degrees of freedom, not included in the biased CV set. And also metadynamics will help sampling transition state in higher line metastable states that are generally poorly sampled in parallel tampering. So this is an example like here, where you like, this is the metadynamics biasing only the fast collective variable. And here we combine it with parallel tampering. And you can see that due to the transition of the parallel tampering, we get much better behavior of the system, and we can convert it much better. Okay. So finally, I've been talking about meta-dynamics. So finally, I want to just mention a slightly different method which I'm working on. This is called variation enhanced sampling. This is a collective variable based on enhanced sampling method based on a variational principle, where we now construct the effective bias potential by minimizing a convex functional given here. And we can show that this functional has a minimum given by this equation here. So what you do in practice, you introduce some linear bias set expansion, like shown here, like some set of basis function, and then you turn this into a convex optimization problem. And this offers many interesting possibilities in the form of the bias potential and the sampling that they can be achieved. So if you're interested in this method here, I have a tutorial in this web link here, where you can look at, let's say, how to apply this method to the actually the same system that we apply here. So finally, maybe this is also something which I have on the GitHub, just a few good resources if you want to learn about meta-dynamics more, is that I list here many different kind of reviews that are kind of useful to read to learn about meta-dynamics. Also, there's a wide range of tutorials available for Plumed. If you just look at this Plumed masterclass, they have a lot of tutorials how to use Plumed and for different aspects, and they go much more into detail than we can do with this tutorial today. So if you're interested in some more details, you can take a look at that. And you can also find other tutorials. And also, let's say, it's always good to look at the manual of Plumed, which you can find in this link here. So finally, that concludes the lecture. So now we're going to move on to the tutorial. And yeah, so thanks for your attention. And I believe there are probably a lot of questions in the chat.